Okay, so good morning, everybody. Thanks for coming in on a holiday. So what we're going to do is we're going to sort of go through this book of Griffiths, which is a pretty incredible book. So this is on the simpler side, but at this stage, we're discussing everything that one should know about what is the standard model. Of course, it doesn't quite construct the standard model for you, but without this knowledge, it will not make sense to talk about the standard model. So you all know this one. The one I have is the second revised edition from 2008. So why am I saying all this? Because 2008 was at a time when the Higgs had not yet been discovered. Okay? So we didn't yet know what the mass of the Higgs was, and we didn't know its properties. So the big change since that edition and now is that the Higgs has been discovered and we know all about it. So if you want to talk about the standard model, you're of course obliged to discuss the properties of the Higgs. You can no longer say that it's something for the future. Of course, the Higgs mechanism, which was already constructed earlier, stands where the free parameter of the Higgs mechanism until that time was the unknown mass of the Higgs. That the actual prediction of the standard model, which is the existence of the Higgs, had not yet been borne out. So that is the big difference. And in addition, compared to that time, which is about 16, 17 years ago, is we know more about neutrino properties, more about the mixing angles, about their mass differences, and so on. These things are known to much better. We have much more knowledge about these things. So if you ask yourself, or somebody asks you, you're on a desert island with only the book of Griffiths, and you have read this, and then you're asked, what is it that people didn't know on the desert island? Then you can say that they didn't know about the Higgs, and they didn't know enough about the properties of the neutrinos at the time that book was written. Of course, in these 16 or 17 years, many other properties, standard model particles, such as B mesons and so on, are much better determined because we have many more experiments and there's much more data, there's much more analysis falling together. So, can someone remind me what we did until the next class? A couple of keywords from where I can pick up. So, let me have a little bit of feedback of what you think we did the other day and what should we be doing compared to where we stood the other day. So, I also answered a question about some of these representations of SU3. So, there's a question about what happens to some of those missing representations in the product of 3 times 3 times 3. And then I found out by looking at Griffiths that there are higher excited states which are accounted for in that. So these are all things that you should read. Not everything should be spoon-fed to you. So the idea is to engage you and tickle your curiosity so that you can go read about these things. There's one other, yeah. Sorry, I can't hear.
Did you have a guess on the Higgs mass from the W and that was the mass?
Not really. We knew that it wouldn't be too high. So if you went back to 2008, let us say, and then there were many precision experiments, and precision experiments, of course, are sensitive to the entire particle spectrum, and there are constraints coming from loops and so on. And so there were allowed regions for the Higgs that it could not be too high, but it could not say precisely where it was. I think at that time there were upper bounds of like 200 GeV, but I can't say for sure. Okay. There were also signs from Fermilab data, which is Tableform data of roughly where it should be. But all that is not good enough because we needed a real direct. Even today, there are some tensions in the Fermilab data. You see this from time to time. This the W mass, the Higgs mass, and so on, and trying to simultaneously determine them. There are controversies from time to time. These are all very difficult experiments. It's not like some straightforward experiment that we do on the tabletop. So if you have large masses of data, and when we say data, what do we mean? We mean calorimetric data, we mean jets that your detector has seen, the directionality, how much energy is deposited here and there, reconstruction, and there's a hypothesis testing. These are all very sophisticated methods by which you say something is actually discovered. So there are many assumptions that go into these things about such hypothesis testing. There are also Monte Carlos which are supposed to model events and so on. So these Monte Carlo simulations always will have some uncertainties, and these uncertainties in some channels can get amplified and then give you some kind of a false negative as to something has gone wrong. So it's an enormous science. Did I answer your question or make it even worse? Okay, so somebody has to remind me where we stood the other day so that I can pick up from there. Okay. Those of you on the front row, of course, are in the firing line. So you can tell me where we stood and then how do we pick up from there. I like your notes. So you have a better than mine. So these are the quarks and quark model and things like that. So we were looking at essentially SU3 representations, SU3 webs, and also the definitions. By the definitions, we mean the lambda I equals 1 to 8, and these are the Gelman matrices. And of course, we know that SU3 contains SU2 also, and so then we have the Pauli matrices. So these are the objects that define SU3 and SU2 matrices. And these are called the generators, and they define generators, and these define something known as a Lie algebra. And when it is exponentiated to an exponential map, it will give you a Lie group, depending on the parameter space. So SUN, as you know, is the group of special n by n unitary matrices. Unitary matrices. So if these are unitary matrices, then you can say about the generators. What can you say about them? That if you have to generate unitary matrices, these have to be Hermitian. Okay? And if it is special, what is this property of speciality? Special means determinant is equal to 1. So then what is the corresponding property for the generators if this determinant has to be equal to 1? So traceless. So from this itself, you can straight away produce the sigma I can be immediately produced. And you all know this, you've done it 100 times. And you can also produce the lambda I from this by permuting the rows and columns, except for the uh, diagonal one. So let me, for the sake of completeness, write down what these are. So lambda 1 should look essentially like the Pauli matrix. So let's write it like this. Lambda 2 is 0 minus I 0. So you see immediately that this thing is traceless, it's also Hermitian, it has to be Hermitian. So lambda 3, anybody guess? 1 minus 1, 0. You can see therefore that SU2 is a subgroup of this, because if you just turn off the third row and third column, you get sigma 1, sigma 2. Now, how do I get lambda 4 from this? As I said, by permuting some of the rows and columns. So let's do that. So just permuting this 0, 0, 0. A lot of this is just being a little clever and figuring out what these are. But you see, it was only until Gelman that nobody wrote it down. Now, Gelman is a contemporary figure. He only passed away 3 or 4 years ago. And he was a physicist, not even a mathematician. So you see, many of these things look very obvious to us, but it took the physicists to actually write these down. Although mathematicians do this implicitly, they do not write it explicitly. Okay, now somebody has to tell me what is lambda 6 and lambda 7. How about this? Very simple. Just think about how I'm getting this. 0, 0, 0, 0, minus I, 0. Okay, very simple. Lambda 8. How about lambda 8? 1, 1, minus 2. My friend here likes this. So this, of course, fixes this, but there's an overall constant which is 1 by root 3, which then fixes the normalization of the lambda. So they all have the same lambda, and I'm going to leave it to you to figure out what the overall normalization is. And u of theta then is given by exponential of I by 2 theta k lambda k. Now this SU3 shows up in a couple of different contexts in standard model. So what we have talked about so far is SU3 flavor, okay, which has to do, it's a global symmetry associated with certain flavors. What are the indices, these flavors? What are the flavors you people like? I like strawberry and buttermilk. What about you all? What flavors do you like? What flavor do you like? You like vanilla. And in addition, what do you like? Chocolate. And as far as this course is concerned, F runs from up down strain, UDS. Okay? UDS. So these are the flavors. We could have also done SU4 with the jump walk, but the jump's too heavy. So except for purposes of drawing pictures, we don't really use that. We might open the window. Okay. So SU3 flavor is a global symmetry, which has, but this was very nice. As we saw from the spectrum the other day, from delta plus plus and omega minus, this predicted the existence of another, predicted, what did it predict? Existence of another, of a, of an additional quantum number, which is, and we gave a name, additional quantum number, and we gave the name color. It's just a name, just a name. It has nothing to do with the color with which we perceive with our eyes. It's just a name, okay? It's like flavor is a name. It doesn't mean that you can taste it with your tongue. Maybe you can, but I can't. Okay? So, an additional color SU3. Okay, we haven't yet proved that it is SU3 or anything like that. We just said that it has to be an additional quantum number, whose name we said is color, and then there has to be three of them. How many of them? Three. Because we needed to antisymmetrize in this internal quantum number in order to get plus or an omega minus. So it is suggested, but it's not a proof that there are three colors. Okay? And then you may guess that there has to be some continuous symmetry associated with these three colors. And what's the name that we want to give it later, which becomes the basis of part of the standard model for the strong interactions, which is quantum chromodynamics. How about the name? SU3, color, C for color. Okay? But in contrast to this, which is a global symmetry, I want to give a name over here, and this is, what name should I give it? If this is a global symmetry, what about this? Local symmetry. Okay? Local, or later we will see that this is gauge symmetry, and we are yet to prove that that nature is like that. That this is part of the standard model, part of the standard. We can't prove for sure, prove it for sure. There are indirect pieces of evidence. So if this was local, then it would have to imply the existence of H bosons, but there's no such thing as C. Okay? Now here, if it is an internal quantum number, and it's a dynamical degree of freedom that is leading to these colors being confined, then the only way of getting theory that is consistent and that makes sense is for it to be a gauge symmetry, and then they'll get the corresponding. Okay? Satisfied? Don't be easily satisfied. But of course, if you ask too many questions, I'll do it as a homework problem. So on the switches here. At least one time should be on.
It's symmetry.
Yeah.
So it implies that some redundant derivative.
No, why redundant? There are additional dynamic degrees. Not redundant. They are dynamical and they're present. Not redundant, but really there. And what are those degrees of freedom? Those are the, so those are the gluonic degrees. Now let me make some general remarks about the existence of symmetries. Almost all of it is known to you, but it doesn't matter. It still helps to hear these things being repeated again and again and again. As we go along, I will give you more and more and more bits of phenomenological evidence that the number of colors is 3, and then this has to be the degree of freedom that you have to deal with. Okay, so the full symmetry here is for SU3 vector times SU3 axial vector, because the underlying theory here is a theory of quarks, which are fermions, which when massless have an additional left and right chiral rotations, and the full symmetry of the QCD Hamiltonian. So QCD Hamiltonian has this full symmetry. SU3 vector times axial vector, where vector is L plus R and axial vector is L minus R, like so. And you can go and read a little bit more on your own as to what these things actually mean. This is broken to SU3 vector with SU3, so this is spontaneously broken. And when SU3 is spontaneously broken, SU3 axial spontaneously. How many generators are broken spontaneously? It is SU3? 8. And so it gives rise to 8 Goldstone bosons. And what are these? No. Gluons are here. Okay. So this has to do with the low energy ground state of QCD, the lightest particles that you observe in the QCD spectrum. And what are these 8 Goldstone bosons? The absolute lightest are the I plus phi minus phi 0. And then you have A plus minus, A bar, and A theta. So this is the pseudo scalar. I'm going to give you all a formula and I'm going to ask you to work out the number associated with this formula. As you can see, I have very extensive notes. And you're all enjoying the weekend. I was working on the course. Just to make you feel it, that's all. Nothing more. Can somebody tell me what the pi 0 decays into? Pi 0 decay. Anybody knows? How many? Each of you has an opinion. How many in favor of one? One photon. Can the pi 0 decay into one photon? That's impossible. Impossible, right? Because if the particle breaks up, then you cannot conserve momentum in the rest frame if it only breaks up. So, what comes after one? Not 0. 2. Is 2 a good candidate for the number of particles that the pi 0 can decay into? What about 3? So Pugarezi doesn't mind 3. Happy Pongal. But the pi 0 doesn't decay into 3 pions. Okay? It's not possible because it's not allowed to decay into 2 pions. because of angular momentum conservation, C, T, T, etc. They won't be decayed to photons. So pi 0 decays into 2 photons. Then I'm going to give you its width. The width. What's the width? Width is the inverse of the lifetime. Okay. It's 7.75 EV, and I'm going to give you a formula n by 0 cubed alpha squared divided by 576 pi cubed f pi squared. F pi is called the pion decay constant, but it actually shows up in the neutral in the charged pion, and it has a value of 92.7 MeV. Can someone compute this for me and give me what this number is? Take your calculator, take Mathematica, do it in your mind, use a slide rule, whatever, and give me the answer. And you evaluate this. M pi naught. Somebody tell me what is M pi naught? Anything else missing? Alpha? 1 by 137. It's an electromagnetic decay, so you should not be surprised that alpha is showing. So somebody tell me what is this? Well, you young people are very fast with typing WhatsApp and SMS. And be equally fast with using a calculator. Hmm? For the width. Oh. Look at this. This is MEV cubed. This is MEV squared, so EV. So this is the formula for the width for decay. And what is the width? Really, how is it related to the lifetime? Width is the inverse of the lifetime. Inverse of the lifetime. I'm asking you to do all these things so that you get an idea of the numbers. Okay. How many?
8.5 to the power minus 7.
What units is that? No, that's not right. Five 76 pi cube. You got everything right? Doesn't matter. Take your time. We're going to be here for 3 hours today. We're in no hurry. Hmm?
8.5.
Unless, of course, I made a mistake in the formula.
That's why this
Hmm? Is it? You tell me. If the answer has to come out in EV, you check the dimensions and tell me. Looks right. Hmm? 2 point. That's correct. So you got this as 2.67 EV. But I'm supposed to get 7.75. So what is the problem here? The problem here is that there is one more factor here, which is NC. And the ratio of 7.75 to 2.6 tells you that NC is equal to 3. NC equal to 3. Okay. This results from something known as the chiral anomaly, which chiral anomaly. So even though it looks like it is an electromagnetic decay, remember pi 0 belongs to the strong interaction spectrum. Okay, so deep inside the pi 0, there are quarks and gluons living in there. Okay, so they are living in there. It is sensitive to the quarks and gluons that are sitting inside the pi 0. and it manifests itself through the existence of this chiral anomaly, which is related to the quarks that are moving around in the pion, and therefore there's a chiral symmetry associated with this quark, and that symmetry happens to be anomalous, and that is why it leads to this particular decay. Okay, it's a very famous example of anomaly, and it is also giving you a signal as to why the number of colors is equal to 3. You can't say that, oh, colors is equal to 3 because of delta plus plus and omega minus, where we just put in a hidden quantum number just because we wanted to anticipate the wave function. Okay, so that you may say is a bit of a cheat. We are just trying to do some clever mathematics and fiddle around with Pauli principle and with statistics, and therefore we invented a new quantum number. And if it is just sitting in delta plus plus and omega minus with no connection to any dynamical process, then somebody may say that you are cheating. Okay? Now, this is a dynamical process of a lifetime where the number of colors actually shows up and it's also equal to 3. Okay, so if somebody asks you in a job interview 3 years from now, how can you show that the number of colors is equal to 3? You already have two pieces of evidence. What are the two? If you speak like that, nobody in the interview committee will be able to hear what you're saying. Yeah.
One is the difference of the factor width of the
Right.
that is the activity of the
Exactly. So you already have two pieces of information which tells you that the number of colors is. Now, why am I saying all this? If it comes to electrodynamics, it's very easy. Electrons, photons interacting, wonderful. Okay. And in asymptotic states of the theory, you see the electron, you see the photon. No great mystery. However, the strong interactions, which are completely non-observative, which is a confined theory with quarks and gluons which can never be liberated. Somebody asks you, how do I know this is not all a swindle? You have to say, look, I know at least two pieces of evidence that NC is equal to 3, one coming from the hidden quantum number and another from the I0 lifetime. Okay? So, good. So that is one thing that I wanted to tell you today. There will be other pieces of information also that we can keep talking about, keep mentioning. Yeah,
Would that be pi squared then? Just putting pi squared into what's this?
maybe. Let's see. Yeah, you're right. Pi is almost 3. It always was. But let me see. This is where did I get this formula from? This paper called pi is pion neutral lifetime. Okay. This is still being measured. There are many experiments to look at it. There's an experiment in Jefferson's laboratory, which is looking at this particular thing. 1985, this is the old paper. That lifetime has been found. Here is the top by measurement. Atherton et al. 1985. This is the old paper. This is anomaly. One of you can look it up and tell me. Bernstein. This paper. This may be the best. It would have been a very embarrassing mistake if that's the case. I can't find it anymore. Okay, you can check. You said pi squared. So my friend here says it's pi squared. Let me take my notes. Here. I've written it as pi cubed in this field. Okay, so you people can another homework problem. Now I'm going to give you a general. Yeah.
I'm not going to do two terms.
Yes.
Just like, 3 comma is quite rejected because of my definition, like the probability is this.
No. As far as I know, it cannot be taken because of it's forbidden by selection rules.
Like higher up or everything is perfect.
More than that, 4 pions may be allowed, but then each time you get an extra power of alpha squared.
So it is up.
So suppressed and probably never observable. These are all good questions. I don't know. I can't tell you immediately. So I'm going to tell you a little bit about the theory of symmetries and what
How do people measure this?
F pi. F pi is obtained from the charged pion and from the charged pion like time. So
So there is a degeneration between.
So you're saying that how do I have an independent measurement of phi? Comes from the charge. Now that is experimentally. Now the lattice tries to measure this independently. Okay? So it's an ab initio determination of F pi. We're trying to solve the strong interactions on the computer. They try to do it, but I don't know how successful they are. They may have some number with very large uncertainties also. Another homework problem for you is the lattice measurement. So since so much of the standard models, so much of the field theory depends on symmetries, we should say a little bit more about symmetries and the origin of these and what their constraints are in the physical theory. So symmetries and conservation laws. What is the mathematical theory of study of symmetries? Group theory, right? And groups can come in one of two varieties. Either they are discrete or if they are not discrete, then they must be continuous. Here there's a further division among discrete, which is they are either finite or they are infinite. Right? Obviously. This finite groups have been completely solved. It's one of the few branches of mathematics or human knowledge where every single thing that you ever wanted to know about finite groups are known. So this is completely solved. So you may be wondering, so this must have been done hundreds of years ago, thousands of years ago. The Greeks, no, it was only done this in the 20th century. Actually, it was checked only in the 21st century. So this is associated with the name John Briggs Thomson. And he has his proofs run into several hundreds of pages, and it was finally checked on the computer by Hales. This is, I would say, about 15 years ago, not such a long time. And this was founded by Galva, you know. Now we have to think that this is a bit surprising. And, which era was Galva from? Galva. Which era? BC, AD, 200 years ago, 400 years ago. Rather recent, 1790 or so. This is only about 250 years ago. He was also a revolutionary and got killed. Mathematics can be dangerous. So this was during the French Revolution and all that, and he was only 21 when he got killed. So you have to watch out. Don't do mathematics when you're too young. So this group theory, all of you, including me, all of us, we memorize some axioms of groups. Right? It's a set with binary operations such that A circle B also belongs to G, A circle B circle B, C is A circle B circle C, and then there exists an identity, so A circle E is A is B circle A, and E is an identity which is unique, so that for every E, for every A, there is an A inverse also belonging to G, so that A circle A inverse is A inverse at A equals E. You've all heard this, right? So it's like a mantra that we want to chant. And A circle B is B circle A, what do you call it? Abelian commutative. Now, if you think it's such an incredibly simple set of axioms, and all of symmetries are actually described by something so simple, so then you would have thought that Euclid should have known this and Brahma should have known this, but they didn't. So it's only very recently that this was discovered because somehow, even though it was implicitly known in many contexts, it was not explicitly written down. But to me, it's an astonishing thing that such a concept actually exists. And it is based on such a simple set of principles, and it's so universal that irrespective of whether the symmetry is continuous or discrete, or finite, discrete, infinite, it's the same set of axioms which are describing all these things. And this commutativity property is also pretty peculiar because you can have a small finite group which may be non-abelian, just some kind of counterintuitive. It's a very small group. Why on earth should it be non-abelian? It is. That's how it is. And you have continuous groups. How come they can be commutative? Well, they are. Now, in terms of its application in physics, symmetries expressed in the language of groups have an astonishing consequence that they imply conservation laws. So, existence of symmetries implies conservation laws, and if you discover a conservation law, then you start to suspect that there must be some underlying symmetry that I didn't know about, and therefore you study a bit more to identify this. So that is how it works in the application of symmetries to physical situations, because in physical situations you have conservation laws, and thereby you uncover symmetries, or if you already know that there is a symmetry, then there's got to be some conservation law. Give me some examples of conservation laws.
Can there be conservation laws without
Hmm?
Can there be conservation laws without it?
That is going to be my next sentence. So, for instance, we know that background numbers is okay, but we don't really know any deep principle which is telling you why background numbers is global. So again, we are going to redefine and push our lack of knowledge from one bin into another bin. At a deep level, we don't know. And when we construct the standard model, we only introduce those interactions which conserve background number. It's almost like fiat that you're doing that, but we don't really know why that's the case. Maybe it's violated at some high level, it's violated at some unobservable level, at a very small level that tomorrow's experiment shows. So, existence of conservation laws and their violations, it can be a window to discovering new physics that you didn't know. So, but this intimate relationship between symmetries and conservation laws, actually continuous symmetries, was expressed in field theory, or more precisely in classical field theory by Noether's theorem. Noether's theorem, which tells you that if you have a continuous symmetry, then in field theory you will uncover some kind of conservation. Now, this is all knowledge that we are picking up today, but later when we actually start constructing the standard model, we will find explicit constructions of conservation laws associated with the specific symmetry. But this is some knowledge that we should have about these things. Sometimes it's conservation laws, at other times you may speak of selection rules. Okay. Selection rules often show up in quantum mechanics. Quantum mechanics because of angular momentum conservation. Angular momentum conservation. Or you may have Hamiltonian H naught, full rotational symmetry. Then you may have an interaction which violates part of it, which breaks to a subgroup. So there are many different contexts in which selection rules will come in handy for you. And we know that for angular momentum in systems with angular momentum. So this has to do with representations of SO3 or SU2, including spin. Then you can do all kinds of angular momentum addition. There's more to angular momentum addition than just saying that if you couple J1 and J2, then you get J1 minus J2 plus J1 minus J2 plus 1. There's more to this because then you also have to compute left Gaussian coefficients. Coefficients, etc. And we saw that if you have symmetry flavor, then you have representations of these. For instance, the 3 and the 3 bar, and then you build up it left using tableau, for instance. And we said that this is global symmetry, and you have other kinds which. But this is not all. So this is an example of the symmetry of the Hamiltonian. Symmetry of the Hamiltonian. Although which Hamiltonian? Strong interaction. Hamiltonian. When mass of the U, mass of the V. Yes. All. However, this SU3 here, color, is a dynamical groups. So even here we will need representations of SU3. So here color defines 3-dimensional representation. The gluons lie in the 8-dimensional. Why should they lie in the 8-dimensional representation? The number 8 is somehow very special for SU3. Why is it special for SU3? It's the number of generators, which means for associated with each of the generators, you have a corresponding degree of freedom, which is a law. And in fact, okay, it's true that there are 8 generators, but the question is, does the 8-dimensional representation also transform as a representation of SU3 or not? Okay. So the question is, do the gluons actually transform as a representation? Transform as a representation. Now, when you write down something like this in angular momentum, you know that J1 that you started out with lies in a certain representation of SU2. It's in one of the YLNs where the N is equal to J1. You know that it transforms. You say J2 transforms in the YLN where L is J2. On the right hand side, you get an irreducible sum. So this is the tensor product that you take. And on the right hand side, you get an irreducible sum. And none of you objected that I should write it like this. Each of you has accepted as an article of faith that each one of these guys actually transforms in an irrep of SQ2 because you have studied this in quantum mechanics. Each one of this must do that. Okay. So similarly, so here if you took a spin half times a spin half times a spin half, what will you get in SU2? You get a spin 0 and a spin 1. Okay. So the dimension of this is 2, dimension of this is 2, dimension of this is 1, and dimension of this is 3. Okay. So you know that when you take irreps like this, you take a tensor product, you get something on the right hand side, which is a sum of irreps. And when you say irrep, the word already is telling you that it is transforming as a representation of this. We have all agreed on that. Therefore, if I take a 3 over here, if I take a 3 of SU3 and a 3 of SU3, what do I get? We did this the other day. Got a 3 bar and we got a 6. So when you write a product like this and express it in as a sum on the right hand side, it means that each of these also transforms as an irrep of SU3, right? So now, if I took a 3 times 3 bar, what did you say it is? I'm trying to answer this question. If you take a 3 and a 3 bar, that's a 3 bar. Let's take it as a 3. That's 3 bar times. So this is a one-dimensional representation, and this is a 8-dimensional. Therefore, the eight objects over here, which lies in the 8-dimensional, has to transform as an irrep of SU3. This is one way of looking at it. And the explicit way in which you can actually construct it is from the structure constants of the DRL. Do people have heard of this word, structure constant? Anybody here has not heard structure constant? Nobody has heard. Those who have heard, please raise your hands. So this actually can be constructed from the structure constant. This is true of any adjoint representation. What's the new word that I just introduced? So this is the adjoint. See, it's very important to know that the pions will transform in the adjoint representation. And you can actually write down the explicit transformation law from that of the. So this was an internal symmetry, but this was kind of an accidental symmetry associated with this. While this is an honest to goodness, real internal symmetry of strong interactions. What other kind of symmetries do you have? Here we are talking about symmetry of the Hamiltonian. Here we are talking about symmetry of internal symmetry associated with the fact that the clock masses are small. Any other very basic symmetries that you people have come across? Space-time symmetry. And these are associated with special theory of relativity. And existence of inertial frames. And how many such symmetries are there? There are. So when you are talking about inertial frames and all that, what's the kind of transformation that you're looking at? Transformations are?
Point here.
That's a bit coming up later, but before that, Lorentz transformation. How many? Maybe six. There are only three Lorentz transformations and three rotations. You can separate. So three rotations. Three. And these together, they leave something invariant. What do they leave invariant?
Space dimension.
So they leave this norm invariant. And then we can define a metric here, which we may need to use later. So G mu nu is diagonal. So one of my collaborators, Peter Minkowski, he is a professor in the University of Bern, now retired. So Peter was one of my earliest visitors here. Sometimes it's a few minutes. So this was a few weeks after I had come here 28 years ago, almost exactly at this time. So Peter came here, and somebody asked him, "Are you related to Hermann Minkowski?" Hermann Minkowski? Oh, Minkowski. This is for the Minkowski measure. So he just said, you have to go up 3 generations and come down 1 generation. What he meant is his grandfather and Hermann were first cousins. But luckily for him, his steps were also correct. 3. He's a very interesting character, rather hard of hearing because he had an accident when he was serving in the army. Some guy let a rocket behind his ear, so he lost his hearing. But he went out to Bangalore, to MG Road. And I was very scared he'd get lost over there. No cell phones and all those days. But he had a mental map. He was telling the auto driver. Here. So people who have some disabilities, they have other senses, sixth sense, I guess. Okay, so that is the metric often that we will deal with.
Meeting has just come.
Please.
A meeting has come back.
So in addition, if you have translations, so now the question is, what are the conservation laws associated with this translations? So we can have space and you can have time translation. So if you have invariance under spatial transformations, what is the corresponding? Fine. And time translation, energy. And if you have rotations, there is rotations, angular movement. So this thing here, the set of transformations that leaves this metric invariant, let's give it a name. What's the name that we should give it? SO. Some name we should give, no? 1, 3. Let's give it like this, which means that one of them will have a plus. Yes.
So what is invariant of what is the condition?
There's no, I don't think that there's any immediate conservation laws.
So there is center of
Center of mass,
which is always conserved.
it may be, but
No,
it
it's
is
the
associated.
it's the conservation law associated.
He says so. I didn't know immediately that
Talking specifically about what is conserved into juices, then I think there is nothing because of some compactness issue.
could be. You people should look it up. Okay? Don't look to me for answers to all these higher questions. It's an important question. I should say something that's wrong. Whereas I don't know, then say something wrong. Okay? I think he's right. I'm not sure.
So it's a standard
Could be. Yeah, you may be right. I'm sure it's discussed in Ryder in all these books. I don't remember. This thing here, this SO31, also has some additional structure, and that is how spin becomes something that is associated with the Lorentz law. So spin is related to this. Spin is related to the structure of this. Now again, these are all advanced topics, but just for completeness, this thing here is isomorphic at a Lie algebra level to SU2 cross SU2. The number of generators here is 6. Here also the number of generators is 6. And from here you can get a theory of spin associated with the Lorentz. In addition, if you have translations together, Lorentz plus translation, Lorentz plus translations, give rise to the Poincaré group. And this thing for particle physics was completely analyzed by Wigner, 1939, and he gave the theory of representations of this thing at that time. And there's, of course, very important work followed up by Harish-Chandra. Extremely important work on the representations of all these groups somewhat later. The thing is, the conservation laws associated with all this are square of the mass and the Pauli constant tensor. Which is loosely associated with spin. Why these things are so fundamental when it comes to but sitting inside this special theory are some discrete symmetries. And what are those symmetries? Important symmetries. Parity, charge conjugation, and time reversal are three important discrete symmetries. Okay, so special theory implies three discrete symmetries. E, C, and E. And it doesn't say whether these are separately conserved or not. Answer is no, because P and C are separately violated by whom? Hmm? By weak interactions. Quite strongly. And CP and therefore T is also violated by weak. Then the other day I mentioned this theta QCD problem, strong CT problem. And you had a question about P and M. I have not found a really good answer, except that I think that it has something to do with non-trivial topological configurations of the group manifold, which, as far as I can see, for U1 is trivial and that is added, but I can't be sure. Then you have a question about electroweak, that is U2. Again, there's a problem there because there are either pions. So you may think that, hey, this thing is just a mu and mu tilde, doesn't know anything about the matter, only has gauge fields. But again, doesn't seem to be the case because of the existence of parallel fermions. Somehow that thing can be reabsorbed in definitions of the mass matrix. I don't know for sure, these are very complicated topics, and if I have to, I have to set aside all this and then read for 2 weeks about those things. Don't have the time. Okay. This is roughly the reason why it is present only for the strong interactions. Of course, you may say phenomenologically it's ruled out because we know electromagnetism doesn't have any violation, therefore it doesn't have corresponding theta term in the action. So that's the one way of looking at it. But then at the fundamental level, you can still ask why am I not allowed to add such a term to the action? And the answer, it seems to me, has to do with the fact that the U1 gauge configurations are trivial and therefore this is what I know about that.
So this P and T are related to the crystal theory.
All three, C, P, T, or all.
So in what way C is related to the crystal theory? Because for the P part, you just reverse the space part and
So that is a very kind of heuristic way of looking at it. If you look at Burns group and then you want to ask what are the representations, then there are the spinor representations, scalars, spinors, vector fields. So that is where the birth is. The birth of any matter is in the representation of the Burns group, either as a spinor or as a scalar or zero scalar or as a vector path, vector field. So it's a transformation to those vector fields, which is underlying property is the Lorentz. And then you have to look at the action of a particular discrete symmetry on that representation. In that sense, that it is bound form. It is, of course, we are accustomed to know there's a mirror and there's a particle spinning like this. Yeah, underlying thing is that it is the spin itself is born out of space. So how will these things show up, for instance, in particle physics applications? Can someone tell me what is the pion, the charged pion this time? Main decay mode? U minus? Any other decay? Nu? E bar. So M pi, 140, and mu, roughly
105.
ME.
0.9.
But you're telling me that this is a more favored decay than this. You're right, but why? Shouldn't you expect that it's the other way? Because the allowed phase is much larger here than it is over here. So this thing here is due to what is called helicity suppression. That's because this is a weak decay. So what is a pi minus? A pi minus is d u bar like that. So this is the w minus. Minus. So the coupling here is a parity violating coupling. Okay? Parity violating. So here this is some f mu or something that's proportional to p mu, proportional to p mu. As Ranjani and I discussed, this is proportional to p mu over here. Whereas here, this is going to be proportional to, what is this here? You know from your particle physics course. 1 minus gamma phi. Gamma mu. What is the meaning of this 1 minus gamma phi here sitting in front of gamma mu? On one of these? Yeah. So that implicitly means that it's violating something. What? So this is the parity violating phi. So now let's look at phi minus. So avant and après, before and after. Normally they say avant and après for air replacement before you put the oil and after. So here. So let's take a phi minus, which then decays into mu bar. And somebody tell me what should be the spin on this particle. It's an anti-neutrino, remember? Okay. So right hand. So it has to be like this. And in order for this to be conserving angular momentum, phi minus is a spin, JP. So this here, so this also has to be like this. So this is right-handed. Now, because the lepton here has a mass, it will not have a fixed helicity. It will have a mixture of helicities. Okay? So, which is then proportional to the mass. So, the probability of this at the amplitude level of this happening is actually proportional to the mass. And that is the reason why, when the mass is present, you can have this happening. If the mass of the pion had exactly been equal to 0, then the amplitude here would have been, so then from angular momentum conservation, this would have been impossible. Okay? So if the mass of the mu had been equal to 0, implies the transition will not happen. Of course, when you write down the Feynman rules and you sandwich this in between, your spinners and you take the trace and all these things, everything is taken care of implicitly by the mathematics and the trace identities, etc. But this is a heuristic way of figuring out why it is that this thing is preferred over this. Because the mass of the electron is so much smaller than the mass of the electron. Therefore, this is preferred and this is not preferred. Even though the phase space is much more to this than this compared to this. It is precisely for this reason that charge conjugation implies phi 0 to 2 gamma is allowed and phi 0 to 3 gamma is not. True charge conjugation. These things were, of course, explicitly shown long ago when it was first proposed by Yang and Lee. What did they propose?
So phi 0 to 3 gamma is also like not about with angular momentum.
So many reasons. There's something called Yang's theorem that is for a rho resonance. So rho cannot decay into 3 pi's for the same reason. The angular momentum and G parity conservation. There are so many of these things. It's impossible for anybody to remember all of this. Impossible for someone of my age to remember all this. Let me just put it that. Yang and Lee proposed parity violation, and Wu did an experiment with 60 cobalt and demonstrated explicitly. These are all the romantic era when given individual to do something and one experiment was to do something, rather than today when you have CMS collaboration, 4,000 authors, and this collaboration, 5,000 investigators. So these are some of the things that I wanted to say today. I have much more to say, but this probably is a decent time to take a little bit of break for about 10 minutes, and then we can resume in about 10 minutes. Is that okay? Okay. So I want you guys to help me, guys and girls, that is, help me with construction of the adjoint representation because it's so let's go back to without Pauli matrices. Okay? Um, sigma I, sigma j for power matrices. Somebody tell me what this is? Hmm? Like, okay. I think there may be a factor of 2, I'm never sure. 2 by 2 by 2 like this. Okay, like that. Now, what can you tell me about this epsilon and jk? Hmm? It's totally antisymmetric. Totally antisymmetric. And this also has a name, which is Levi beta. And each of the ijk go over 1, 2, 3. Supposing I want to construct a matrix Ti whose jk element is epsilon and jk. I can do that, no? It's very convenient. Each of these is 3. I have 3 such matrices. It's a 3 by 3 matrix. And each of the elements of this 3 by 3 matrix is determined by epsilon and jk. Nice, isn't it? Now you will see that this Eitj is so constructed will also satisfy the same algebra. That is what is meant by saying something transforms as a representation of a Lie algebra. The statement means that that set of objects will satisfy the same algebra. Okay? That's really what is meant by the representation. And the dimensionality refers to the dimension of the matrix, which in this case is 3 by 3 matrices. Right? Now, supposing you want to do this for SU3, then what are the matrices that we had? Lambda I, lambda j. What is the corresponding, again, probably divided by 2. You should always check whatever I'm writing. On the right hand side, what would you expect? Lambda k by 2. And here, let's put an I. Hmm? But not epsilon, it will be more than that. It will be some. And these guys here are called the structure constants. And what can you say about these structure constants? Obviously, by construction, this thing here is antisymmetric in I and J. So the antisymmetry between I and J is manifest, whereas the full antisymmetry actually you have to be able to prove. Now, analogously, and how many such are there? I, J, K run over 1, 2, 8. Now you can construct Pi, which are now 8 by 8 matrices whose jk elements are given by I, or you can know about the I, F, G. Then again you will see that this Pi, J will satisfy the same algebra, K. And this is the definition of the adjoint representation. The adjoint representation is that representation which is built up from the structure constants and has this transformation. That is the definition of adjoint. And we will need, for our purposes of constructing gauge theories, that the gauge fields actually lie in the adjoint representation. There are two places here. You can come here, come to the front. Yes. Hey guys, we are taller. You can move to the back. Back.
This part of the board.
No, that's why I'm telling you to go there. Right. Come up here. You won't be able to see. I know, because when I come to seminars, when I want to sleep, I sleep. Now, in the SU2 case, we had this beautiful property. You'll recall that in the SU2 case, even though we started out with that, you can have a T plus minus is E1 plus minus I T2, where the Ti are now sigma I2. We had this thing that this T plus T minus we saw was 2 T3 and T3 T plus minus T. So we said that look, this here, this conjugate pair here closes on the diagonal generator. And what is this diagonal generator? It's an element of something. It's an element of the give me a name, Cartan subalgebra. So this thing here closes into the element of the Cartan subalgebra, and this here gives an eigenvalue equation. So this SU2 generalizes easily to SU3, as we saw. So this SU2 can generalize to SU3. Where we have two diagonal generators, T3 and Y. And then there are these complex conjugate pairs, which are T plus minus, U plus minus, U plus minus. And then there are these corresponding commutation relations. Which is that any of these x plus with one of these, what should I call it? C for Cartan subalgebra, Ci will give plus minus. It may have some numerical constant times x plus minus, and x plus x minus will give some element of the Cartan subalgebra. So SU2 kind of generalizes to SU3. SU3 starts showing more structure. And the amazing thing is that SU3 can generalize to the entire, bit of an exaggeration, but say, generalizes the entire family of semi-simple algebra. Then whatever you have will break up into a part, which is the Cartan subalgebra, and then whatever is left behind will break up into complex conjugate pairs, and those complex conjugate pairs will have the very nice property that element and its conjugate will give a member of the Cartan subalgebra, and the commutator of any of those with a member of the Cartan subalgebra will give you an eigenvalue equation. So that is the beauty of this whole thing and how it generalizes. Now you remember that in the SU2 case, all we needed was a one-dimensional space. So what determines the dimensionality of the space on which we put representations? Or you can have this, etc. Okay. What determines the dimensionality of the space on which you can put any representation of SU2? The number of diagonal generators. Okay. So in the case of SU3, there's only one diagonal generator, and that is why the third component of the angular momentum is so important. The M, L, M, and the M, L and M completely determine which state you're in. Okay, so it's the dimensionality of the Cartman's of algebra, okay, which fixes for you this very nice property of the number of dimensions that you need. So for SU3, what do we need? For SU3, we needed a 2D space. Okay. And we saw that the three-dimensional one was this, and we saw that the 3-bar was this. Then we saw that the 8-dimensional one was this. But we already saw that there was a new, so this is a 3, this is a 3-bar, this is 8. But we saw a new feature here, which is not present in the previous case. That is, you can have a multiplicity of more than one. Okay. How many independent vectors do you need to go from any one state to any other state in a representation? Leo was telling me about some very nice packages that are available to study algebras using Mathematica. What he didn't know is that some of your brilliant seniors, along with me, have already written a book on that. It's published, European Physical Journal, Saudi, not here. So, this is 5 of us, myself, Amitabh Lahiri from Calcutta, and 3 former students, undergrads. We have publication on how to generate all these Lie groups, the algebras, all these things using Mathematica. There are other Mathematica packages that we have used as a backbone. Part of it is our own, part of it is our examples, etc. So I can send you the link if you like on how to study all these applications. So I'm asking you a question over here. There's 6 of these guys over here. And how many vectors do I need in order to go from any one state to any other state? It's a 2-dimensional space, so you need only 2 vectors. So it seems as if this is overdetermined, which means that one of them is a linear combination of the other. Okay? So you have only 2 linearly independent vectors which can take you from any state to any other state. Okay? So the number of linearly independent vectors you have is same as the number of elements in the Cartman's of algebra, and that is known as the rank of the algebra. What is the rank of the algebra? He's really picked a very bad place to say. It's the dimensionality of the Cartman subalgebra. What is the Cartman subalgebra? It's a collection of simultaneously diagonalizable generators. In the case of SQ2, how many elements are there in the Cartman subalgebra? SQ2? No, that's the total number of generators. How many are diagonalizable? Only one, JZ. Okay. In the case of SU3, how many generators are present? 8. How many are simultaneously diagonalizable? 2. What's the rank of SU3? Dimension of the Cartman subalgebra, which is 2. And the number of linearly independent vectors, also 2. So out of these 6 over here, they are complex conjugate pairs. So out of the 3, only 2 are linearly independent. So why am I screaming myself hoarse about all these things? Because this is the data that you need in order to generalize to any semi-simple. Except that this is still a little too simple. Here, the way in which I have drawn these figures, everything is a nice equilateral triangle. This is a very nice, regular hexagonal form and so on. If we know that because we have an explicit representation for the Gell-Mann matrices, that the lengths of these vectors can be explicitly calculated by just looking at these things and eigenvalues and all these things. You can fix the lengths and show that is an equilateral triangle. Is it so that for any algebra, each of these is called a root, by the way. Each of these are called roots. So you have two members of the Cartman algebra, you have six roots. Okay? You have three roots and three complex conjugates. That's six roots. Out of these three roots, we will need only two of them to be linearly independent with one linear combination of those two guys. What is the term that you would like to give the two linearly independent roots? The guys who are in my class, they can't answer this question. But okay, people who are not in my class last year, what name would you like to give to these two roots? I'll give you a name. They are called simple roots. Okay. So the number of simple roots is equal to the rank of the algebra. So I just said that for the case of SU2, the case of SU3, the simple roots have the same length. The basic root, which lies in the adjoint representation. Obviously, there will be, I'm not talking about high dimensional representations. The roots happen to lie in the adjoint representation. Okay. And they have the same length in the case of SQ3. So, there are two possibilities. Either the simple roots have the same length, they don't have the same. So, whenever the roots are of the same length, simple roots are of the same length, such algebras have a name. And that name is, they are called simply laced algebras. Simply laced. Simple roots have the same length. So, in order to specify an algebra in terms of the simple roots, what is the data that you need? You need the length of the vectors and you need something else between those vectors. For any two vectors, you need the angle between those two. So in this case, you can choose these to be the simple roots. Okay? In which case the angle will be 120 degrees. So as you see, please check these facts also. Now I ask you to open your minds and generalize this, and you can tell me now what are the possibilities of going beyond this SU3. You go to SU4, and how many generators will SU4 have? 15. How many? What is the rank of SU4? So the dimension of the Cartan subalgebra is 3. How many simple roots will you have? Have 3. So 15 minus 3 is 6. That is 12. 12 divided by 2 is 6. So you'll have 6 roots of the plus type, of which only 3 will be simple. Okay? Now you will need to know the lengths of those 3 simple roots and the angles between them. And in this three-dimensional space now, you will have any representation that you like. You can start out with a four-dimensional representation, which will be like tetrahedron. You can have a 4-bar, it should be an upside-down tetrahedron. And then you can have the adjoint representation, the beautiful diamond in this three-dimensional space with simple vectors, angles between them. Any state you like to any other state. Except that at the origin now, you have a multiplicity of 3. That's how it works.
So is the rank always 8 minus 1?
For the unit systems. So you can do this for SU3, SU4, SU5, you can do it for SU999 if you like, no problem. Any SUN you can do it. It will have the same structure irrespective of which SUN. It will always be simply based. You can always find the number of members of the Cartan society. You can always find the number of groups. And this thing goes through. Now you start telling me what are the further generalizations that you can have. So SU2 generalizes to SU3, generalizes to SU4. Okay, and then this series is called AN. So SU2 belongs to A1, A2. There's again a mismatch. If you say A4, it's actually SU5 because the N stands for the number of simple groups, alternatively the number of members of the company. I'm going to stop here. Is it okay? Overwhelming or it's okay? No problem. So this is AN. And what did we say about these groups? That they continue to be simply laced. Okay? They have to be simply laced algebras. Simply laced means that the length of the uh, simple groups are equal. What is the opposite of something being equal? Not being equal. Right? So that is another thing we can do. The next generalization you can ask is what happens if the lengths are not equal. So if you have three roots, three simple roots, and they have three different lengths, what do you say?
Open this.
No, we now forget about SQL. Now I want to invent a Lie algebra where I say that I have three simple roots and I want them to have three different lengths. Is that possible? No. You can have at most two different lengths. So you can have at most two different lengths. Why? Because of this various sets of commutation relations which are needed to invent a Lie algebra. You can either have all the simple roots to have the same length, or at most they can be of two different lengths and of very specific ratios. And I've got what they are, half and 1/3. Right? These are the only two ratios allowed among the lengths of the simple roots. Okay. Abhishek here will remind me what are the different lengths. Yeah, you. What are the different lengths that are allowed among the simple roots, and what are the different angles allowed among the simple roots? Actually, even this is not arbitrary. If the ratio is half or 1/3, then the corresponding angle is also known. It is fixed because there is some kind of a quantization rule on the lengths and on the angles between the simple roots. Okay. This is all explained in the wonderful books of Dr. I, or Khan, or Slansky's tables, or other wonderful. Okay. I should send you the link right now. So semi-simple Lie algebras, at most you can have two lengths, and if the lengths are known, then the angles are also fixed.
Is simple Lie algebra the condition of imposing simplicity of the Lie algebra is it equivalent to it being simple?
No, no, not at all. What comes after A? After A, B. Then, then, then. So there is something called a classical series, and it stops at B. Okay. So A N B N C N B N. Okay. This and this are simply laced algebras. A and B and B and C are not simply laced. This is what is called the classical series. Classical series. The orthogonal groups, they fall in some of them. Orthogonal groups of dimension 2n, they come in this. Then orthogonal groups of odd, they come in one of these. And then there's another So these are what are called Lie algebras, by which we need the generators of the Lie group. Okay. We take the generators and exponentiate it to get the group. You take the group and look at it in the vicinity of the identity element, then you get the algebra. Clear? Group near the identity is the algebra. Take the algebra and exponentiate it, you get the group. Okay. So that is the relationship. So we use the same symbols also. We are using the same for the group as well as the algebra, keeping in mind this distinction. In some books, you will see uppercase for the groups, you'll see lowercase for some funny Greek calligraphic for the algebra, depending on the book. Okay. So A, B, C, and D. So you can have SO2N, where N can be anything. The corresponding algebra is called Bn. It's also simply based. Whereas this B and C are not simply based. One of them corresponds to orthogonal groups in 2n plus 1 dimensions. The other one corresponds to what are called symplectic groups. You know symplectic groups? Symplectic groups here, in what context? Hmm? Classical mechanics. So that's what preserves the metric 0, 1, minus 1, 0, which is what shows up in Hamilton's equation. So the canonical transformations of some classical mechanics systems, they enjoy the symmetry which is called symmetry. So this is the end of the classical series. Something is not classical, what is it? Hmm? What is it? It's called exceptional. So then, at the end of the classical series, you start to have the exceptional series. And the exceptional series doesn't run all the way to infinity, but it's finite. E6, E7, E8. What comes after E? What comes after A, B, C, D, E? Then F. And F, O. And after F comes G, 2. And after G comes H with a 0. See, it's also decreasing. So there is no H. So this is the exceptional series. E6, E7, E8 are also simply based, whereas this here, they are not simply based. Okay? These are very complicated objects, but they apparently show up in some branches of physics. God knows why. These, the classical series n is not constrained. N can be any integer, and the actual structure of their transfer algebra and simple groups and all is different. So the complete classification given by Kaplan, where he has the relationship between the angles and the lengths. If you solve them completely, then this is all that you can get. This book of Kant is one of the most fantastic books ever written. Everything is explained over it. R.N. Kant, it's written for particle physicists. R.N. Kant. For those of you who are more mathematically minded, Jacobson, and of course, I should not forget. I can only say it. These are so the relationship between length and angle as a diagrammatic representation, as a diagrammatic representation. The full constraint equation can be solved, and the solution of those constraint equations is what gives rise to this A, B, C, D, E, F, G series. Okay? And this is expressed in terms of what are called Denkin diagrams. So Dinkin solved this problem diagrammatically. Again, I think the news is about 20 years old. Still keep trying at my age. Guy is finished everything at age of 20. What is it? So anyway, so you never heard of Dinkin again because after that he moved into probability theory. So that's Dinkin. But this also allows you to compute all the subalgebras. Compute the subalgebras. So I'll just give you this extempo discussion on some of these. Okay. Now let me represent SU2. How many does it have? Pattern subalgebra? One. So very boring. So thinking diagram is just that. What about SU3? Hmm? Two. So two circles. But if I didn't connect them, it would be like SU2 cross SU2, right? So, but if I connect them, then it is called the Dinkin diagram for SU3. Okay. Now, how can you see that SU2 is a subalgebra of SU3? You just erase one of the dots and you get that. Okay. SU4. Yeah. So if you erase one of the dots of SU4, you will see that SU3 is a subalgebra. If you erase a middle dot, then you see SU2 plus SU2.
Maybe arrange them linearly.
Hmm?
Maybe arrange them linearly.
Very good question. The rules of this constraint equation that you have between this does not allow a dot to be reconnected to some other dot. It's a very good question. So it's an algorithmic approach. Given the rules, and the rules are dictated by the commutation rules. They are ironclad. You can't do anything about them. Because without that, the algebra is not the algebra. It's something else. Once you say it's a B algebra, then you require it to satisfy those commutation relations. Then the constraint equations and the classification scheme will allow only the solution. In Jacobson, he actually discusses this question. Jacobson, write it down. Repeat slowly after me. Jacobson. It's a Dover paperback. You can get hold of it. I have one in my office, but I only give it to people who are nice to me. So you have to make your choice. Yeah. No. Very good question. So it means that these simple roots which are there, see, in the case of SU2, there was nothing, only one root up and down. In the case of SU3, there are two of them which takes you this way and that way. Okay. In the case of SU3, you start to imagine, and it's not difficult because you can embed this. And there you can see that those simple roots have some very nice properties of which planes and hyperplanes they lie on, and the kind of mutual relationship between those. Okay. So you asked a very good question, and that's the answer. Okay. That why is this middle dot? Why is it connected to these two guys? And these two guys are not connected to one another. Of course, there is a certain ordering also implicit, which says that this here is connected to both. So the Dinkin language tells you all this. Okay. What about SU5? 1, 2, 3, 4. Okay. Now again, you can start erasing dots and you can figure out. I'll give you one more example of SO10. SO10 is of its even order. Okay. So its Cartan subalgebra, its rank is 5. But its Dinkin diagram is this, which links to your question that there's this middle dot over here. It talks in a non-trivial way to this guy as well as to another one, to this one. Okay. Now you look at this and you tell me, many of you dark matter types who will be doing various models for dark matter and all, grand-unified models and all. You will want to know what are the subgroups of S10. Look at this and tell me what are the subgroups of S10. What happens if we erase this dot over here? SU3 cross SU2 cross SU2. Okay, if you erase this guy, you get an SU5. SU1. If it is this middle guy, again you get an SU4. Then there's something known as an extended linking diagram, which gives you the maximal subalgebra also that you can use this technology. So just to complete, the BNs and CNs look like this, BN and CN. So this here means that all these roots are of the same length, and there is one root which is of a different length. Okay, and this two lines here indicates what is the angle between this unequal one and this. Okay, so the convention is in this case all the equal roots guys are longer and this one is shorter. There's another possibility where all the equal roots guys are shorter, the other one is longer. So that is the relationship between B and C. So similarly, you can finish up this discussion. So the key ideas are the algebras themselves and the representations of these, which have to be represented in this multidimensional space whose dimensionality is given by the rank of the algebra.
So these are just for compact groups.
Yes. Very simply, yes.
So is it necessary and sufficient for the linking diagram of a unitary group to be a straight line?
Yes. Because those are somehow the simplest from the point of view of the algebras.
So 1,3
Yeah.
can be written as SU3 plus SU2.
Yes.
Then in that case,
In some simple cases, it may be possible. See, this is again the algebra. Okay? We are talking about the group. So there the depends on the parameter space. So what happens that for SO31, it is not a compact group because the velocity of a particle can never be equal to the speed of light. So the parameter space is not compact because it is not bounded and closed. There are all these issues which are of mathematical importance, and it was very difficult to classify and study them, and that's why Harisundar's work is so important, because he solved that problem once and for all, for instance. So where was I? I'm completely lost. Roots, equation. Okay, so the other key thing is how to take tensor representations and what are called branching rules of representations. Okay. Now, let me say a few words again about branching rules. So let's look at SU3 web over here. Now, SU2 is a subgroup of each one of these, right? So the 8-dimensional representation of SU3 can break up into 2 plus 2 plus 3 plus 1. Okay? It's not overwhelming, right? So this is a 3-dimensional representation. SU2 is a subgroup of this, which means that you're only looking along this axis. So this 8-dimensional representation along this axis, this is the 2 of SU2. This is another 2 of SU2. And these 4 states over here, pi minus, pi 0, pi plus, is a 3-dimensional representation. And the co-ether that is sitting over here is the same. So this is the simplest way of understanding how you can get branching rules of a representation of a larger algebra when you view it as branching under a smaller subalgebra of the larger. But for purposes of this course, luckily, we don't have to do anything more than SU3 because standard model gate rule is SU2 cross U1 times SU3. We don't have to bother about any other algebra in this course. unless of course you have the ambition of embedding this thing into some other group like SU5 or SO10 and so on. Now this SO10 has even more complicated representations. It has something called spinorial representations, which of course we definitely don't need to discuss. But if you people pay me handsomely for it, then maybe I will have an extra cost. Subjected to receiving payment on my PayPal. Otherwise, I want to do one slightly off-topic discussion because it is very implicit in everything that we do. So I want to have a discussion around that so that I can told you this once and for all, and you won't see it later. Right? Tell us that you actually do this. Now, all of us are very confident we know how to use final rules and all, but I want to give you a very quick overview of how to get final rules in a sort of a rapid way using path integral representation. It's a very nice derivation. And I want to make some comments that you will often not see written anywhere. That's the reason why. And I'll also need it for something else that I do. Are there any questions about everything that I have said so far? Yes.
So from the diagram, I can see.
Yes.
From the
It's very difficult to define, which is very good. There is something known as a killing form that you have to define on the algebra. It's possible to do it. And a killing form is the only way in which you can give the notion of a length. Because a norm of a vector necessarily has to be positive vector. So the scaling form introduced by killing is what the same as killing vectors, same killing. So he introduced this notion which is important to define something on the length. Sorry, use. Describes very nicely. Anything more?
How do the decay diagrams help us determine the lengths and angles?
There's a formula which tells you if it is two lines that joins them, then you know what it is. If it is three lines that joins them. And there's only one such, which is the G2 algebra is the only one which has the three lines joining that relation. It's part of the Cartan classification of the algebra. Now, in your other courses, QFT course and particle physics course and so on, all of you mainly draw Feynman diagrams and you just draw this thing and then you call it a Feynman propagator. But somehow we all seem to be happy and we think that that is enough. That we don't need to know any Feynman propagator in a sense is a two-point function. If you go to your quantum field theory book, it will say it is the vacuum expectation value of high moderate product of phi at x1 and phi at x2. So it is what is called a two-point function. Somehow the two-point function seems to be enough for all the purposes of our particle physics. Do you know of any other example in life where it somehow suffices to know only the two-point function and nothing else? And everything else that you wanted to know about that theory can be expressed in terms of the two-point function. I am talking about a theory with only one species of particles. If you have a theory with more than one species of particles, fermions, H bosons, is that, you will have a two-point function for each one of them. have a propagator for pion, boson, have a propagator for the engaged particle, but each of them separately is a two-point function. Okay? But somehow the two-point function is very crucial. Now, do you know of any other example where things work that way, where only the two-point function suffices? Now, when I hunt for my what bottle, you people are going to think of the answer. What happened to my water bottle? Yeah, that did work. Check. It's gone now. Any other thing that you know in life where only the two-point function is enough? I'll give you a hint. It's named after a very great German mathematician. German mathematician. You have to tell us, who was this great German mathematician? He used to appear on the 5 mark notes of Germany. Of course, you were not born before the time that I have seen it. Before the euro, they had the German mark and Deutsche mark. So it had a picture of this great guy. What is the unit of magnetism, you know? Answer me. Yes, there's one. Another one. Gauss. See? Now I can hear the hint. You know of something that Gauss invented, that there's only the two-point function, is the only piece of information you need. You also need the mean, but in addition, you need the two-point function. What's the two-point function called? Think again. It's called the standard deviation or the variance, right? So the Gaussian distribution is completely determined if you know the mean and you know the standard deviation. You don't need anything else. If you want the 16th moment of the Gaussian, it is some product of the same standard deviation again and again. The sigma is enough for you to get anything that you like. Okay? Any correlation, any correlator that you need, any moment of the distribution you need is expressed as some power of the two-point function, maybe the standard deviation or the variance. So our friend, the Feynman propagator, is a two-point function, which somehow is like the variance or somehow like the standard deviation, and every single correlation function that you need will become a product of these two-point functions. Okay? So that's the reason why the Feynman propagator is so important. But then, what does it have to do with Gauss? Somewhere deep inside this, there is something that looks like a Gaussian distribution that you have integrated in order to be able to express the generating functional of the Green's functions in terms of this particular thing. So that's the point that I'm trying to say over here. And how do we actually go about this? We go about this by looking at the object that is known as W of J, which is the vacuum transition amplitude. Give me the full name. Transition amplitude. In the presence of source. And it has a representation not in Minkowski space, but in Euclidean representation of this, WE, is something that looks like this, which all of you I'm sure have done in your PhD course. You have written this as a sum over or an integral over all possible configurations of something. What is something? Somebody remind me. What is the something over here? Right. D4x. Lagrangian. Phi bar. Euclidean plus J bar. Close all these braces. And the connected Green's function. How many of you have seen this? Is there anybody who has not seen this? Or we have taken QFT, right? Anybody has not taken QFT? We're taking now. You will learn this. Okay? It is just, I'm just giving you an advance preview of what is the basic object from which you get Feynman rules. And why is it that the Feynman propagator shows up no matter what you do? So here I missed a page, but it doesn't matter. So the connected Green's functions Gn of the nth derivative of J. And then what should I do? Turn off the source. And this over here removes the disconnected pieces. So let us do this for an illustrative example. Now somebody tell me what is L naught. So this is for a scalar field theory. Only one species right now, L naught. Can somebody advocate a Lagrangian for me? Field Lagrangian. Field Lagrangian. Very good. I like this guy. So I like all of you, but anyway, at least so far. Minus 1/2 squared. And what about Li? And our favorite interaction.
So,
Yes.
what is the index feature? The index feature.
Euclidean. So you are aware of Euclidean.
Actually, the unpart of Lagrange is that Euclidean or because.
Very good question. Okay. Question for you, Lawrence, and you come back and tell us. I think this is the
I
unperturbed.
think both terms should have the derivative term should have otherwise it will not cause like
You may be right. But it's almost genuinely standard. Okay. So you want the minus sign over here?
either is
Okay. I guess this is still in the Minkowski where it was written. Now W, you're right. Actually, it's still not yet Euclideanized. So let's see here. It gets changed a bit later. So W0, okay. W of J, we write this as exponential or, because it factorizes, you can write it like this, D4x of Li delta by delta J. This is a nice trick. That the W now factorizes into a piece where the interactor is sitting up in the exponential separately. And then there is this exponential of the free part W0 J. So if you can have the path integral representation, because of the fact that there's an exponential sitting here, I think once again I lost something. No, I'm not yet lost because I'm going to write this as W0 J as the integral over all configurations of the exponential of the P part plus J part. So far, so good. Hmm?
What is the is the Li function?
What this means is that it is to be written like this. So here this is Li of phi. So this is a trick in field theory that is used where the interaction part is written wherever you see phi on the left hand side, it's phi to the 4 on the right hand side. Okay. So if you say Li of delta by delta j, it means minus lambda delta by delta j to the 4th power. That's what it means. And you have to do it like this in order to generate the final series, the perturbation series. So this is the way in which you generate the perturbation series. So this thing over here has to act on the right hand side because here it is derivatives with respect to j, and on the right hand side you still have a j sitting over here, and we are yet to write it in a way where this thing can act on what is on the right hand side. Now comes the fun part. So, so we know what is L naught and we know what is J phi. And here we have this d lambda phi, d lambda phi, d lambda phi, which is sitting over here with this integral of d4x. And I want to do something to this. I don't like this way in which it is sitting with a d lambda phi and a d lambda phi. Okay. So if I don't like it, what is it that I want to do? I want to move this d lambda onto this. And how can I do that? I can't just do it like that unless there is an integration taking place. And if there is an integration taking place, what is the kind of integration that you want to do in order to shift this derivative onto this? What is that called? The procedure? It's called integration by parts. So that this thing here becomes box. The other term, of course, is the mu squared lambda, mu squared phi squared. It stays as it is, and this thing here is going to become mu squared phi squared. So now this thing becomes the following is W naught J, then becomes so this W naught J becomes an integral over C phi, like it was before, exponential of minus r times integral d4x d4y phi of x a of xy phi of y plus integral d4x till j of z phi of z, a of x phi. Now, what is this k of xy? This k of xy is an operator as a delta function delta of xy, the minus box. Now, if you forget about all this d4x, d4y, all these things, this looks pretty much like a Gaussian integral. Gaussian integral is something. What does a Gaussian integral look like? It's ax squared plus bx, right? So this is what sits inside the Gaussian integral here, where the role of x is played by the field variable and then the x over here is one more field variable, and then there are these coefficients like a and b, which is all the stuff that is coming from this d4x, d4y, this k function, and this b here, the whole b. This j. So in order to carry out this Gaussian integral, what do you have to do?
Getting K.
Yes.
So doesn't like sign of the box change because it is integration by parts?
Yes, you have to check all this out. Okay. So up to those signs, it is maybe wrong, but for the moment it's. So when you have an integral like this, what is the next thing that you have to do? When you have an integrand that looks like this, with an ax versus b, you have to complete the squares and then do the integration. Okay. So in order to complete that square, then you will generate a constant term over here which has nothing to do with the integration. Okay. So all the integration will be taken care of, but in the process of completing the square, you will end up with objects that involve these coefficients a and b. And let me give you the answer, and you can go and work this out for yourself. You'll see how beautiful it is, this particular way of doing these things and understanding how the Feynman series arises through this process of Gaussian integration. So, and I'll tell you the important properties that you need in order to do that. W naught of j is, it will turn out that apart from a numerical constant associated with this integration over all possible paths, the j dependent part will be something like this, which is an exponential of r integral of x of y, j of x, delta of xy, j of y. You see, in this process of completing the squares, now you have ended up with a bilinear in j. None of the stuff that we had earlier had a bilinear in j. Okay. But in this process, we have ended up with a bilinear in j and an object that is called delta, which is related to this k over here, which is your Klein-Gordon operator multiplied by this delta function here. And we can say explicitly what this is. We can say that this delta is such that integral d4y a of xy delta of yz is equal to delta of x minus z. So in other words, this delta is behaving as an inverse of this operator. So if delta is behaving as an inverse of this operator, what must it be? This is the inverse of this operator. Now remember that your Feynman propagator also satisfies an equation. It has to satisfy an equation. Feynman propagator belongs to the free non-interacting theory. It is a green function of the theory. Therefore, it satisfies an operator equation, which the operator that you have, rather has its own equation of motion, and it is the Klein-Gordon operator which operates on the Feynman propagator in order to produce what on the right hand side? It has to produce a delta function. Now, you know a green function of any operator is such that when a differential operator acts on the green function, it generates a delta function on the right hand side. And that is not enough to specify a green function. What is needed? A green function, of course, has to satisfy some kind of an operator equation. But in addition, you have to say something more. Exactly. You have to give the boundary conditions of a green function. A green function is not determined unless you give the boundary condition. And the boundary condition that is given for the Feynman propagator is the I epsilon prescription. Okay? And the I epsilon prescription is such that you can actually do this Euclidean notation that my friend was asking for. Without that I epsilon prescription, you cannot turn the axis in the or do the wick rotation, because then you would have collided with the pole. Okay? But because it has one pole here and one pole here, one above the real axis in the left, below the axis on the right, you can do the wick rotation. That's the reason why that I-epsilon description is needed. Otherwise, now a lot of this is formal theory that we don't really need in our day-to-day applications and computations. But all the great stalwarts have done all this in the past 100 years, done all this, and all this information is needed to make this theory something that's reasonable and good and works. If you give a wrong description in the last 50 years, all of us have been doing a wrong description, then we had a disaster. We would have never come to this. So obviously we've been doing something right. And then you can say that the delta function is integral d4x. And now this is the Euclidean version. Please check all these things for yourself. Okay? I'm sure you can all do it. Is okay. So this is Chaitanya's question. It's not still over here. It's a plus a squared. And all this is stemming from the fact that the Gaussian integral exponential of minus ax squared to bx dx is equal to exponential of b squared divided by a times square root of pi by a. This is the basic Gaussian integral from minus infinity to infinity. Now observe the structure of this. The linear term in x inside the integrand had only a coefficient b, but in the process of completing the squares, you ended up with an exponential of b squared. And that is how we have this bilinear, where is it gone? This bilinear over here. Okay? This constant over here, a, has shown up in the denominator, here. I'm not talking about the exponential, but I want you to observe this, that it shows up in the denominator over here. This thing could be easily generalized to a two-dimensional integral, three-dimensional integral. Instead of just constants, you could have a matrix over here and you could have a matrix over here. And you can do a corresponding integral with these matrices also. And if you did that, I'm going to ask you, what do you expect to see over here in the square root of? You want to see a determinant, square root of the determinant. That's a crucial thing. You'll see square root of the determinant. Now, all this amazing stuff that we have done over here, which is your entire PhD course condensed into 30 minutes. Okay? You tell your other teacher. So this was for a scalar. And since you guys are so brilliant, you have already told me that the square root of the determinant of a matrix A appears in the denominator. Appears in the denominator. So what is the next generalization that we need to do? What are the other species of particles that we may want to deal with in the standard model? Standard model, the only scalar particles are Higgs. So if you went back to 2008 to Griffiths, then there could have been no book at all, right? But he did write a book. So what are the other particles present in the standard model? Pions. Pions and gauge particles. So do you think it's possible to do such a procedure for pions also? What would be the changes? The changes, of course, would be you don't have a quadratic line Gaussian operator, but instead what do you have? you'll have Dirac. And instead of bilinear and phi, what will you have? You'll have a psi bar and so on. Okay. But then you can't quite do this procedure uh, like we did with scalar fields. Okay. So here, everything that we did over here, we assumed that we could treat them as doing mathematics over the field of reals and complex numbers. Okay. You can't do the same thing with fermions. So what would you have to do in order to include fermions in such a discussion where you want to set up a Euclidean generating functional for fermions, you want to break it up into an interaction part and a free part, then you want to carry out this kind of a Gaussian integration. This Gaussian integration is the most amazing thing. The whole Feynman series now comes out of this. See, now you have this expression for W naught of J, which has two powers of J like this. Your interaction will act on this W naught of J and keep pulling out Feynman propagators. It's like in the Gaussian distribution, the 44th moment will be some power of the variance. Similarly, any endpoint function that you compute to whatever loop order you want will just keep producing Feynman propagators. That is why Feynman propagators, the basic building block of field theory in perturbation theory, plays the role of the variance or the standard deviation of the Gaussian distribution. Okay. So far, so good for scalar particles. What do you do now if you have fermions? What is this thing over here? Somebody mentioned Grassmann variables. So there's another kind of a number field invented by Grassmann, obviously, which are anti-commuting objects, and you can do the same kind of Gaussian integration using Grassmann fields. Anti-commuting. And you can do everything, and it all comes through very beautifully, except for one crucial difference. And I want you to look at this blackboard and tell me where you expect that difference to show up. Obviously, you will have to get some bilinear like this in the source. It'll be a Grassmann source, by the way. A bilinear source. You will get a propagator for the exact field. So this part of the expression will look the same. There's only one thing that will change. And what is that? Exactly. So this determinant will show up in the numerator. Determinant will appear in the numerator. That's just astonishing. But you know, people didn't bother about all this. They still did field theory. You may say that, look, this is an artifact of using path integral representation. I'm an old-fashioned guy. I don't like path integrals. I use canonical quantization. And I could have left just as happily, which is all true. However, when it comes to quantizing gauge theories, this thing will play a role. This thing will play a role because in gauge theories, besides the particle spectrum, which is fermions, gauge fields, there's something else that will happen, which is pretty amazing, and it's a feature only of non-Abelian gauge theories. It's not a feature of field one. This very peculiar thing happens where you need the path integral for gauge fields, and you have to do all this, and then additional degree of freedom will show up, not in asymptotic states, but in loops. And what is that thing which will happen? It will lead to the appearance of ghosts, the called Fourier-Popov ghosts, in order to make the quantum gauge theory consistent with it makes sense. The way in which the ghosts play a role is through this kind of Grassmann algebra, and you have a determinant that appears in the numerator, and then that's how the Feynman rules for these ghosts will have to be accounted for because of the way they appear in the path. There's no other way of doing it. There is a messy way of doing it in canonical quantization also, but practically useless. So that's the story in the gauge theories, which is what we will have to do when we are doing the standard model based on gauge theory. I think we have had enough. Everybody's had enough, or people want to go on for another 2 hours or so. Okay, so I'll stop now, but let's take a few minutes for questions and relax and wind down. Okay, you always have to wind down. Suddenly hold out your class, not like that. Any questions? Is all this clear? Clear? It will look very similar. It will formally look similar, where there will be a corresponding source, will be a Gassman source for the field, for the fermionic field. And in fact, you have to have a source and a kind of conjugate source, one for, see, you can't just add something like this for fermions. So if you have a fermion, say psi, then this thing has to be anti-Grassmann, and then it has to be a psi bar, which will have Grassmann. Okay? So it's a little more work, but then you can do it easily, and then get what
Jane, you were seeing any of the observables or computations that we have. We always set it to 0, right?
after taking derivatives.
Yes. So does this have any physical significance? Like, can we choose J to be anything or?
These are notions which actually come from statistical mechanics. And this source idea was introduced by Schwinger. So he developed a whole theory based on sources, which is equivalent to the Feynman representation of field theories, but it is calculationally very useful. In order, we could have done everything without path integral, we could have done everything without sources by using weight rotations and weight fractions and all this. Equivalent. This is a telegraphic way. You may think that this is the Instagram of particle physics, okay? Or the Snapchat of particle physics. Problem with Snapchat is after 5 seconds it disappears. Let's go for Instagram. So this is the most rapid way of getting to the heart of the matter. Given a theory, given an equilibrium, given an interaction, how do I get the final rules? How do I know that this is correct? And also it gives me the possibility of accounting for gauge theories and accounting for ghosts through this determinant construction. Now, yeah.
So when you wrote like the two ingredient object, like why did you write the ingredient there? Is there any other form like substrate that you could have written by ingredient?
The Euclidean path integral can be shown to be the generating functional of Green's functions only if you do this Euclidean thing. Okay? Then, if you read Cheng-Lee, the first few pages of Cheng-Lee explains very clearly why you need to do this. This formal object that you write, why is it the generating functional for Green's function? You can write it, but you have no way of relating it to something that is required unless you do it in Euclidean space. Okay? All the other contributions except the ground state, vacuum to vacuum transition amplitude. Remember, that's the first word that I used. That it is the vacuum to vacuum transition amplitude can be shown only in the Euclidean. Otherwise, it will get contributions from other states.
In any other space,
It also has something to do with convergence issues and all of that. See, we all have to start somewhere, no? So this is the starting point for us to say that for standard model to be able to write down the final rules and so on. I have to start somewhere. So this is one way of starting.
So we wrote the endpoint Green's function as a derivative and J equal to 0.
Right.
So if we write that for one point, it looks awfully like the relation between a Lie algebra and a Lie group. The one point being, so is there any kind of association?
So, of these path integral representations as a manifold structure to be able
Yes.
to use. We are not sure it will create a manifold structure. If it does create a manifold structure, then
Since
we
we
are
can
sure.
differentiate, it definitely has a manifold structure.
I mean, it's only at the zero.
So in a neighborhood around 0, we have a manifold structure. Not the whole space, just the neighborhood.
But when you want to think of something as a real algebra of a corresponding linear cube,
Forget the Lie algebra and Lie group structures, just introduce the manifold and tangent space structure. Then it works.
but you want to be sure that these sort of tangent vectors at zero would create the flow of the entire path space. You won't be sure.
Unless and until the group is compact.
I don't think that would lead to complete.
No, no, just because you see a derivative and an exponential, it doesn't mean it has all these things. They're all just, some operations of calculus that we do for a particular purpose. V group and all, you have all those commutation relations between the generators. There's no such thing. Anything else? Of course, meet on Thursday at 10 o'clock. Of course.
Okay.